Very good morning. My name is Komal from BSc Second Year Chemistry Honors. Now I read a chapter of a physical chemistry, a thermodynamics second. Let's start. Introduction Niels for the second law and the French statement of the law. The first law of thermodynamics had contained strict limitation. To overcome this limitation, a strong need was therefore felt to introduce another law called the second law of thermodynamics. A few limitations of the first law and as a consequence some definition given to the second law are briefly given below. First, a major limitation of the first law of thermodynamics is that it merely indicates that in any process there is an extent equivalence between the various forms of energy involved, but it provides no information concerning the feasibility of the process, whether the process is possible or not. For example, the first law does not indicate whether heat can flow from a cold end to hot end or not. All that it tells it is that if this process occurred, the heat energy gained by one end would be exactly equal to that lost by the other end. Similarly, the first law does not tell whether a gas can diffuse from low pressure to higher pressure, or water can itself run uphill etc. The second law supplies answer to our questions by stating that all, sponta- all spontaneous process like the flow of heat from hot end to cold end, diffusion of gas from high pressure to low pressure, or the flow of water down a hill etc. are thermodynamically irreversible. First definition. The term spontaneous process used in the above definition means a process which can take place without the help of any external agency. All the natural processes, some of which are mentioned in the definition above, are spontaneous process. However, it may be mentioned here that the term spontaneous does not give any idea of the rate of process. Whether the process takes place fast or slowly, all that it implies is that a process can occur without the help of an external agency. The first law states that when heat is converted into work, the work obtained is equal to the heat absorbed. However, it has been seen from experience that heat absorbed cannot be completely converted into work without leaving some change in the system or the surrounding. For example, the heat produced in a locomotive is not fully utilized in running the train. A part of it is lost to the surrounding or waste in overcoming the friction. Hence, the second law is also stated as follows. The complete conversion of heat into work is impossible without leaving some effect elsewhere. Second definition. Beside the above definition, a number of other definitions have also been given to the second law of thermodynamics. The two important ones are: first, it is impossible to constant a machine function in cycles which can convert heat complete into the equivalent amount of work without producing some change elsewhere. Third definition. Second, without the use of an external agency, heat cannot be itself passed from a colder to a hotter body. Fourth definition. The term functioning in cycles is introduced in above definition to indicate that the machine must return to its original state at regular intervals so that it can function continuously. Further, it may be recalled that in an isothermal reversible expansion of an ideal gas, delta U is equal to 0 so that Q is equal to W. The work done is exactly equal to heat absorbed by the system. In other words, in the process, heat is completely converted into work. However, it is important to observe that this conversion is accompanied by an increase in volume of the gas so that the system has undergone a change. A number of other definitions have also been given to the second law of thermodynamics, which we will come across in the succinct sections of this chapter. The fraction of the heat absorption by a machine that it can transform into work is called the efficiency of the machine. Thus, if Q is the heat absorbed and W is the work done, then the efficiency of machine is given by and W upon Q. The machine used for the conversion of heat into work is called heat engine. In the order to bring about this conversion, the engine absorbs heat from a heat reservoir at a high temperature called the source, convert a part of its work and return the remainder to the heat reservoir at a lower temperature called the sink. Carnot cycle and its efficiency. In order to calculate the efficiency of any heat engine, study cartoons in 1824 devised a technique called Carnot cycle. A cycle is a process in which a system returns to its original state after a number of successive changes. A process conducted in the manner is called a cycle process. The engine chosen by the Carnot, called Carnot engine, for the purpose of the calculation of the efficiency was a hypothetical one and cannot be achieved in the actual practice. It was selected because it could be subjected to simple thermodynamic treatment. It consists of a cylinder containing 1 mole of an ideal gas as the working substance and fitted with weightless, frictionless piston so that all the operations in the cycle are carried out reversibly. For this reason, it is also called reversible heat engine. The cylinders is supposed to be insulated or all sides expect at the bottom so that the heat can flow to or from the system only through the bottom. Further, it is supposed that there are two heat reservoirs, one at a high temperature, so called source, and the other at a lower temperature, sink is called sink. If the some operation is carried out by placing the cylinders in the source or the sink, it can exchange heat with it and hence the temperature remains constant so that the process is isothermal. On the other hand, if during an operation the cylinder is placed on the insulating material, no heat exchange can take place between the system and the surrounding and hence the process is adiabatic. The Carnot cycle consists of four different operations which can be represented on a pressure volume diagram. The operations are carried out as shown in briefly figure. Isothermal expansion. The cylindrical containing 1 mole of ideal gas occupy a volume V. It placed in contact with the source. The gas absorbs heat Q2 from the source and expands isothermally and reversibly till its volume has increased to V2. The path of the process is represented by the isothermal curve AB since the gas is ideal. The work done W1 by 1 mole of ideal gas will be given by minus W1 is equal to RT2 log V2 upon V1. Further, for an ideal gas, the work done is equal to the heat absorbed Q2, so that minus W2 is equal to Q2 is equal to RT2 log V2 upon V1. W1 has been taken as negative and Q2 as positive by the latest SI conversion of a sign. Second, adiabatic expansion. The cylindrical is not now cylindrical is now removed from the source and placed in perfectly insulating material so that the gas now expand adiabatically and reversibly. Work is done in the expansion, but since on heat enters or leaves the system, the temperature must fail. The reversible adiabatic expansion is continued till the temperature has fallen to T1, which is the temperature of a sink. Suppose the corresponding volume become V3. The path is shown by the adiabatic curve BC. The work done W2 will be given by minus W2 is equal to CV T1 minus T2 minus CW T2 minus T1. Where CV is the heat capacity of a ideal gas, hence again W2 is negative and the usual convergence of a sign. Isothermal compression. The cylindrical is now removed from the insulating material and placed in contact with the sink, the heat resistor at the lower temperature T1. The gas is compressed isothermally and reversibly till the volume decreases from WV3 to V4. The process is represented by the path CD. The work done is taken as positive by the usually convention of science and hence will be given by W3 is equal to RT1 log V4 upon V3. During the operations, an amount of a heat Q1 exactly equal to W3 will be returned to the sink at T1. Heat has been given out by the system using the appropriate convention of sign Q1 will be negative and W3 will be positive, so that minus Q1 is equal to W3 equals RT1 log V4 upon V3. Adiabatic compression. The cylinder is now removed from the sink and placed again on the insulating material. The gas in the compressed adiabatically and reversibly along DA till the initial state A is regained. The temperature of the gas rises from T1 to T2. The work done is positive by the convention of sign and will be given by W4 is equal to CV T2 minus T1. As a result of this source for operation, the system has returned to its original state so that a reversible cycle has been completed. The net work W that done by the system will be given by RT2 log V2 V1 plus RT1 log V4 upon V3. Since V1 and V4 lie on one adiabatic curve and V3 and V4 lie on another, such that the result come W upon Q2 is equal to T2 minus T1 upon T2, which gives the efficiency of Carnot cycle or engine. Carnot theorem. From equation 13, it is clear that efficiency of a reversible heat engine depends only upon the temperature of the source and the sink and it independent of the nature of the working substance. Another important observation to be made from the above derivation is that the work done in the cycle is only the one involved in the isothermal operation because the work done in the adiabatic operations second and fourth cancel one another. Further, as discussed earlier, the work done in a reversible isothermal expansion from A to B is maximum where the work done on the gas during the reversible isothermal compression from C to D is minimum. Hence, the total work done by the system is maximum for the specified condition and therefore the efficiency is maximum. The result that follows from the Carnot cycles is called Carnot theorem. It may be stated that the efficiency of a reversible heat engine depends only upon the temperature of a source and the sink and is independent of the nature of the working substance. In other words, all reversible heat engines working between the same two temperatures and the same efficiency. Further, it states that the efficiency of a reversible heat engine is maximum for the given temperature. Since the quantity T2 minus T1 upon T2 is always less than unity, the efficiency of a heat engine is thus always less than unity. In view of the above discussion, the second law of thermodynamics is sometimes defined as follows. A heat engine absorbs a certain amount of heat from the source, converts a part of it into work, and returns the rest to the sink. In other words, it is impossible to convert heat completely into work. Further combining equation, we get the net work done by the system is equal to the net heat absorbed by the system. Putting the value of W in equation Q2 minus Q1 upon me Q2 is equal to T2 minus T1 upon me T2. Hence, the efficiency of a heat engine may be given by any one of the following expression and is equal to W upon me Q2 equal Q2 minus Q1 upon Q2 equal T2 minus T1 upon T2. This result derived for a reversible Carnot cycle lead to the introduction of a new thermodynamic terms are called entropy. N is the efficiency of the heat engine. W is the net work done by the system in calories. Q2 is the heat absorbed from the source in calories. Q1 heat absorbed returned to the sink in calories or joule. T2 temperature of source in degree Kelvin. T1 temperature of a sink in degree Kelvin. Now thermodynamic scale of temperature. From our earlier studies, we are familiar that the thermometer is contracted most commonly by taking suitable amount of mercury in a glass bulb at the end of a capillary tube and make zero. When it placed in contact with ice and make markings hunger when it is placed in boiling water. The length between the 2 points is the divided into hunger equal part called degree. The scale of temperature thus obtained is called Celsius scale of temperature. However, because different liquids expand to the different extent, their coefficient of expansion are different and also they do not expand uniformly over a given range. Thermometer constructed by using different liquid will show different numerical values of temperature between their fixed point. For example, a body may show a temperature of 28.7 degrees Celsius with mercury thermometer but may show 28.8 degrees Celsius with an alcohol thermometer. The problem was solved by the study of properties of gases. It was found that an ideal gas or a perfect gas gases to exist at a temperature of minus 27 to 73.15 degrees Celsius. This temperature was called 0 degree absolute. The scale developed on the basic is called perfect gas temperature scale and is found to be independent of the ideal gas taken. However, based on the efficiency of a reversible heat engine, Lord Kelvin was the first to develop a scale of temperature that was independent of nature of the gas taken in the heat engine. This scale of a temperature is called thermodynamic scale of temperature or Kelvin scale of temperature. It found to be independent with the ideal gas temperature scale. The basic of development of the scale is briefly discussed below. Suppose there are two constant temperature heat reserve, one acting as a source and the other as a sink, and a reverse heat engine operate between them. The temperature of each reserve of the new scale may be taken as proportionally to the quantity of heat absorbed from the source and the heat lost of the sink. If Q2 is the heat transfer from the source and Q1 is the heat transfer in the sink, then if the temperature on thermodynamics or Kelvin scale are represented by the Q2 and Q1 respectively, we shall have Q2 upon Q1 is equal to theta 2 upon theta 1. Thus, this ratio of a two temperature has been defined in a manner independent of the nature of the thermodynamic substance. Taking the reciprocal both the side of equation first substance, subtracting the result from unity we get put theta 1 is equal to 0, then find q2 minus q1 upon q2 is equal to 1. This implies that the 0 on the Kelvin scale is the temperature of a sink for a reversible heat engine whose efficiency is unit, which is capable of converting heat completely into work. But from equation 14, it may be seen that it is possible only at absolute 0 on the ideal gas scale of temperature. This leads to conclusion that the Kelvin scale and the gas scale are identical. Provided gas is ideal, the temperature on the thermodynamic scales are therefore expressed in terms of degree Kelvin. Further, it has been found that the lower fixed temperature is taken as equal to the triple point of a water's 273.16 Kelvin. The Kelvin is exactly equal to Celsius degree for the region. The temperature on the absolute scale in which the melting point of ice is taken at 273.16 degree is often referred to as degree Kelvin. It may be concluded that the thermodynamic scale of temperature as defined on the basis of second law of thermodynamics is more basic than that of basic on the ideal gas because fluid can be used. However, the ideal gas scale is more practical for laboratory use. Concept of concept of entropy as a state function. For a reversible Carnot cycle working between temperature T2 and T1, it had seen that T2 minus T1 upon T2, where Q2 is the heat absorbed isothermally and reversibly at temperature T2 and Q1 is the heat lost isothermally and reversibly at temperature T1. The above equation may be simple as Q upon T is equal to constant. We conclude that the heat absorbed or lost isothermally and reversibly divided by the absolute temperature at which the heat is absorbed or lost is a constant quantity for a particular system. Further, in equation second, Q2 is the heat absorbed at temperature T2 and Q1 is the heat lost at temperature T1. If Q1 were the heat absorbed at temperature T1 would be written as Q2 upon T2 plus Q1 upon T1 is equal to 0. Now consider any reversible cycle ABC. It may be regarded as being made up of a number of Carnot cycles. Draw across the diagram as starting from A and going through all the cycles successfully from A to B. It can be shown that all paths inside the closed the curve ABA cancel each other, leaving only the Jing-Jang path, which is almost the same as the path ABA of the reversible cycle by making each Carnot cycle smaller and increasing their number. It can be made to corresponding more closely to ABA. The reversible cycles can therefore be regarded as being made up of infinite number of a Carnot cycle for each of these cycles we have. The infinite number of Carnot cycles delta Q upon T is equal to 0, where delta Q is a very small quantity of the heat absorbed at temperature T during the small isothermal change of reversible process. Further, the above terms may be divided into two parts, one for the path A to B and the other for the back path B to A. Thus, the implied that the total value of the quantity Q upon T for the path A to B is equal to the total value of the quantity Q upon T for the reverse path B to A. Here it may be concluded that quantity Q upon T is a state function. Its value depends only upon the initial state and the final state and is independent of the path. Obviously Q upon T is the change in the value of a quantity for or a function having some defined value at A and B depending upon the value of pressure, volume and temperature. This quantity or the function is called entropy and is usually represented by the symbol S. Thus, if S is the value of entropy at A and SB is the value at B, then we must have Q upon T is equal to SB minus SA is equal to delta S, where delta S represents the total change in entropy in going from the initial state A to final state B. Hence, entropy may be defined as a state function, the change in the value of which from the initial state to the final state is equal to the quantity Q3. The total heat absorbed reversibly and isothermally in going from the initial state to the final state divided by the absolute temperature at which the heat is absorbed. From equation 6, the entropy change may be defined directly as the quantity of heat absorbed isothermally and reversibly divided by the absolute temperature T at which the heat is absorbed. It is important to note that as entropy is a state function, therefore the value of entropy change during a process should not depend upon the path, whether the heat is absorbed reversibly or irreversibly during the process. However, since the derivation of the above result is based upon Carnot cycle in which the heat is absorbed reversibly, the expansion 6 for the entropy change is valid only when the heat is absorbed reversibly. Thus, it is better to use the symbol Q reversible in the place of Q. The expression 6 may therefore be written as delta S is equal to Q reversible upon metric. Further, as entropy is a state function, a small change in its value can be represented by ds, hence we may write ds is equal to Q reversible upon metric. Unit of entropy. From the expression delta S is equal to delta T, del Q upon T, it is obvious that the unit of entropy will be calories per degree. If heat is expressed in calories, further entropy is an extensive property. It is therefore important to mention the quantity of a substance involved. It is usually expressed for 1 mole of the substance. Hence, the entropy units are calories per degree per mole. It heat measured in joule. The unit of entropy will be joule per degree per mole. Energy change in a reversible process. Suppose a process occurs under completely reversible conditions. The heat is absorbed by the system reversibly and heat is lost by surrounding also reversibly. If a Q reversible is the heat absorbed by the system reversibly, then the heat lost by the surrounding will be Q reversibly. If the process takes place isothermally at the absolute temperature T, First, entropy change of the system will be given by delta S is equal to Q reversible upon T. Second, entropy change of the surrounding will be given by delta S surrounding is equal to minus Q reversible upon T. And total entropy change from the combined system and the surrounding will be Q reversible upon T minus Q reversible upon T is equal to 0. Thus, we may conclude that in a reversible process, the net entropy change for the combined system and surrounding is 0. There is no net change in entropy. Entropy change in an irreversible process. In any part of the process is irreversible. The process as a whole is irreversible. Suppose that the total heat lost by the surrounding is Q irreversible. This heat will be absorbed by the system, but the entropy change of the system does not depend upon the heat actually absorbed, but it depends upon the heat absorbed reversibly. On the quantity Q reversible, thus, if the heat is absorbed isothermally by the system, at the absolute temperature T, the entropy change of the system will be delta S system is equal to Q reversible upon T. Further, suppose that the loss of a heat irreversible by the surrounding takes place infinitely slowly reversibly and isothermally at temperature T. The entropy change of the surrounding will be given by minus Q irreversible upon T. The total entropy change for the combined system and the surrounding will therefore be Q irreversible upon T minus Q irreversible upon T. Now we know that the work done in a reversible process is the maximum work. Further, as the internal energy is a state function, the value of Q delta U is the same whether the process is carried out reversible or irreversible. Combining result 4, 5, we concluding that combining this result with the result given the equation 3, we observe delta system plus delta surrounding greater than 0. Thus, it may be concluding that in an irreversible process, the entropy change for the combined system and the surrounding is greater than 0. On irreversible process is accompanied by a net increase of entropy. Since all spontaneous processes are thermodynamically irreversible, first definition of second law of thermodynamics, it may be stated that all spontaneous processes are accompanied by a net increase of entropy. This is also one of the very common statements of a second law of thermodynamics. The result of for the entropy change in a reversible process and them in irreversible process may be combined together and put in the form delta system plus delta S sounding greater than equal to 0. Where the sign equal to stand for the reversible process and the sign greater than for the irreversible process. The extent calculation of a total entropy change during an irreversible process when heat flow from a body B at high temperature to a body at a lower temperature when both in the contact with it may be carried out of a fluid. For the heat lost by the body be represented Q irreversible. The flow of heat may be allowed to take place infinitesimally close to that of absorbed by the body A reversibly and isothermally at T1, which may be represented Q reversible. The entropy change of a body B will also depend only on Q reversible. Hence, entropy change of body B is equal to minus Q reversible upon T2. Entropy change of body A is equal to plus Q reversible upon T1. Delta total is equal to Q reversible upon T2 plus Q reversible upon T1. Q reversible is equal to Q reversibles bracket 1 upon T1 minus 1 upon T2. Kelvin inequality. I discuss about for the irreversible process. The result given in equation 9 may be written as delta S system plus delta surrounding greater than 0. Also equation we have delta S surrounding is equal to minus q upon t. Delta S system greater than q upon t. Delta S system greater than minus delta S surrounding. Delta S system greater than q dq upon में d. Express 4 6 are called Kelvin inequality. These equations show the irreversible process are accompanied by the increase of entropy. This is further illustrated with the help of the following two examples of irreversible process. First, spontaneous expansion. For irreversible adiabatic expansion, suppose the system undergo irreversible adiabatic change, then the dq is equal to 0, hence the Kelvin inequality delta is system greater than 0. The entropy of system has increased further, dq is equal to 0. This means that no heat is transferred into the surrounding, thus delta surrounding is equal to 0 and total entropy change. Delta ds total is equal to ds system plus में delta s surrounding is equal to differentiation of system. Delta system greater than 0 and delta total greater than 0. B. Irreversible isothermal expansion. We know that the when a perfect gas expands isothermally, its internal energy remains constant, du is equal to 0. Hence, according to first law of thermodynamics, du is equal to dq plus dw. dq plus dw is equal to 0. dq is equal to dw. If the gas expands freely into vacuum, no work is done so that dw is equal to 0. Substitution in equation 7 given dq is equal to 0. Hence, by Kelvin inequality, ds system greater than 0. Further, as dq is equal to 0, this implies that ds surrounding is equal to 0. Hence, the total entropy change as its above system case delta is total greater than 0. Second, spontaneous cooling. Suppose heat is transferred from one system at a higher temperature T2 called the source to the another system at lower temperature T2 called the sink. If a heat dq leaves the source and enters the sink, entropy change of the source dq minus dq upon T2, entropy change of the sink plus dq upon dt. Total entropy change ds total dq upon t1 minus dq upon d2 is equal to dq 1 upon में t1 minus 1 upon में t2. As t2 greater than t1, comma delta s total is equal to positive cooling. Transfer for heat from hot body to cold body is accompanied by the increase of entropy. Now, second part of a thermodynamics read in another video. Thank you.